Hello and welcome back to the channel. I've been very busy lately, so I'm sorry I didn't post for a while because I was designing some printed circuit boards. And in fact, may I remind you that this is the kind of service I still offer. So if you'd like to design some PCBs with me, please feel free to contact me via my website. Anyway, in this video, we're going to talk about fabrication issues associated with printed circuit boards. And in particular, I want to have a look at the most common mistakes that I see engineers do that come up during design reviews. So to kick off our list, the first item is actually not knowing your requirements, and that often applies to radio frequency printed circuit boards and sometimes also to FR4 printed circuit boards, which are the standard types, and that I see come up when the engineer just simply isn't aware of limitations that they would likely encounter during fabrication. So the best case, or the best thing to do in this case, is to go to one of the fabrication websites, such as PCB and actually have a look at what's available. So let's say I want to make 100 by 100 millimeter PCB, and let's call it 2 layers, and then you can actually look into limitations within this. So, there are 14 layers maximum, and let's say I was designing a high frequency PCB for antenna, then I would want a different substrate material rather than FR4 because it's very lossy. So I would use Rogers material, and we can see here that the only 2 real options we've got are Rogers 4003C or Rogers 4350B. So very often I see designs that come up with some unique substrate that just simply isn't available. So let's have a look at an example of a board layer stack. And what I've got open here is a 6-layer PCB, which is a typical board layer stack for medium density high frequency printed circuit boards. It's got perhaps Ethernet or USB lines and such. And in this case, you can see that the distance between top layer and polygon pores of mid layers is 0.1 millimeter, so you can see it here. And 0.1 millimeter or 4 mil is the kind of distance that I recommend for good cost efficiency. You also need to make sure that your board layers are symmetric. And what I mean by that is that there are 6 board layers in this case and not 5. And likewise, if I were to remove this layer, the Ultium designer will automatically delete the associated layer number 2 and 3. So the Ultium design already takes care of it for you. And the reason for that is to make sure that there is no warping on a PCB, or in other words, that it doesn't bend on itself like a pan-fried potato chip. And PCB warping is a quite common fabrication issue, which you may also encounter if you don't have equal amounts of copper on layers. So for example, if I have a solid polygon pore on mid layer 1, but only a couple of traces on layer 4, then this is a problem as well. So you really want to make sure that you use polygon pores and fill up all your empty space with copper, which you can connect to 0 volt and then stitch them with wires. So the point that I'm really trying to make across here is that it is your responsibility as of designer to make sure that you're using adequate board layer stack that is manufacturable. Also, for electromagnetic compatibility, you really want to make sure that this distance between signal and ground layer is minimized, because this is your return path, which was going to be mid-layer 1 in this case, and you don't want it to be far. Let's have a look on another example. So in this case is a much more complex PCB, and that's got 14 layers, but you can see that I followed the same pattern in terms of signal, ground, signal, ground, signal, ground layout to make sure that every signal layer has an associated ground plane no more than 4 mil away or so. So in most cases the distance between ground and signal plane, so in millimeters, that would be around 0.07. So that's even smaller than the previous example, and you may want to check with your PCB manufacturer what kind of tolerances they really want you to have. Number 2 in my list is to avoid wire-in pads. Wire-in pads are quite established technique for high-dense and high-frequency printed circuit boards. However, they are very, very expensive, and I tend to find that even using micro-wires is more preferable in cost than using wires in pad. Let's look at an example. So here I've got a very small wire, which is in fact just 5 mil in hole size, so that's the size of the drill, and 10 mil in diameter. So this wire is much smaller than the typical recommended PCB design guidelines that we looked at earlier, but it is still much cheaper than the wire-in pad. And the way it's also done here is that it's what's called a buried wire, in that it only connects layers 1 and 2. So that means that I can still route on, let's say, layer, well, already have a trace there on another layer, and that is not going to collide or interfere with the wire, because it only spans for 2 layers. And likewise, you can do the same for the outer layers on the bottom side, so layers 13 and 14 in this case. The other thing that's worth noting is that my PCB pad does not interfere with the outer dimension of the wire, which is the solder ring, and that is done in such a way that there is not going to be any manufacturing or fabrication issues. Now, you sometimes can or have to push your wire closer, so then it is as close as this, and that is still not technically a wire-in pad, but now your soldering pad can actually leak into this hole, and because it's or it can leak into the soldering ring. So it's not a good practice, and some PCB fabricators will treat it as a wire-in pad. So you best double check before you do that. So number 3 in my list is to always make sure that your components have 3D bodies associated with them, and that if you create a new component, you must make sure that you add a 3D body and check that it actually matches the footprint. This is a very common mistake that I did quite a few times back in the day. It's just I would create a footprint for, let's say, QFN 30, but I wouldn't realize that this footprint is for QFN 30 with a pitch size 0.4, while my IC is a QFN with pitch size 0.5, so it's actually physically smaller than the device I'm actually using. And I wouldn't realize this up until I actually download a 3D model from a manufacturer, put it against my footprint, and then I'll see, oh, it's much larger. So very important to do that, and it also applies to things like connectors, because you just very often can't tell the difference by looking at the 2D sheet or on the PDF. The number 4 in my list is knowing how to treat mixed surface mount and through-hole designs. So let's look at another example. In this case, I have mixed surface mount and through-hole components placed on a printed circuit board. Here you can see that as long as they're all on the same layer, there's not going to be an issue, because as long as you insert your through-hole components top to bottom, all the soldering pads will be on the bottom layer. So, and if we look at the bottom layer, there are no components there, except for this component, which is R243. So this brings us to the point that I was trying to make earlier, is that this distance between the soldering pad of a through-hole component and a soldering pad of a surface mount component must be no less than 1.5 millimeters, and in this case is even more than that. It is 2.5 millimeters approximately. So if I had, for example, this resistor much closer than that, for example here, or even you can visualize it better if it's placed there, then you can see that there's just simply not enough space for the automatic through-hole soldering process to occur, because once it's inserted this through-hole resistor, there's not going to be enough clearance between the soldering iron and the surface mount component, so it will collide with it, and it will probably cause a fabrication issue. So don't do that. Number 5 common mistake is not defining the no routing areas. And the no routing areas are most commonly encountered when you say you have a fixing pad, which your PCB is fixed to a chassis with, and you would typically have some sort of a soldering pad around it, which is fine, but what designers don't usually account for is the washer that may be mounted there as well, or any other metal-like material. So you really need to define the no-go area around this pad, which would be the maximum size of washer or anything else that needs to be here. And it's as simple as that, because you shouldn't route there or place any components, and otherwise you will get short circuits on the PCB. And this point can be illustrated if we look at the M2 component here. In this case, this is an M3 size screw that's going to be mounted into the chassis and attach this PCB into the chassis. And in this case, it's a very good example, because you can see that there is a clear outline made in the outline layer, that beyond which you should not be placing any components or doing any signal routing, because this is where your screw is going to be attached, and the screw, the area under the screw is exposed copper, so that it can make a good connection as well to this copper area. Now, if let's say I had this component much closer, which I could do because it's connected, so it's not going to cause any DRC issues, but you can now see that it's clearly inside this area and inside the outline, so the mounting screw will now clash with this component. And potentially one way to improve this would be to even include a 3D model for the mounting screw, so that you will clearly see where you have a clash. So the next point in the list is not actually related so much to fabrication, but it is one of the most common mistakes I see on printed circuit boards, so I decided to include it in this video. And that is not defining matched lengths or differential traces on the schematics or PCB design files in general. Then what happens is that you don't really have a DRC issue, but none of your DDR traces are length matched and the PCB simply doesn't work. So it's kind of a fabrication issue, but just not in the same way. Now let's look at an example of how to actually do that. So first of all, you really want to define all of your differential traces with this sign, and that's very simple. You just click on the differential pair parameter and you add it where your differential traces are. And in Altium Designer, for differential traces, you must include _p and _n into the title of your differential trace. Otherwise, the Altium Designer will not understand what on earth you're talking about. It will assign the labels automatically to this. So that's one example. And the other example, when you have, let's say, DDR traces, you want to include a box and draw a box around this, and you do it by creating a blanket, and then that will create this. And what else you do? You also attach a parameter. So this is the parameter setting, and in the parameter setting you just need to clearly define the net class of the DDR group that you setting the length matching to. Then you need to head into design rules, and this is actually one of the best ways to see whether this board has been designed by someone professional or someone who is a novice, because when you open up the design rules for the first time and you only see the default settings, well, you know that the designer hasn't actually played with them. So if you open the Altium Designer and you look into design rules and you see something like this, and you have a lot of different settings, then that's a good sign. So in Altium Designer you have your matched length settings here, and this is where when you assign DDR matched lengths, you will create rules for each group of DDR signals, and you can set the tolerance either by distance, so that would be 10 mil, or you can set it by delay, and that's talking about high speed rising falling edge differences. So yeah, that's effectively all you need to know. And then you can do this for each of the nets. For example, you can also do it for the Ethernet and USB, which I do recommend doing, but you can set a much wider tolerance as opposite, for example, to DDR clock, which has a very, very close tolerance. So this is a match length differential clock for DDR signals, and you can see the tolerance is set to just 1 picosecond, which is good. So once you've done that, the length tuning you can do by playing with those buttons. So one is for single-ended trace and the other is for differential pair trace. While we're here, the other thing that's worth looking at is the impedance, and this is where you actually set the target impedance for your rules that you will use in a PCB design, and you can add them here. So you have, in this case, I'm using two impedances, which are 50 ohms and 90 ohms for differential impedance. So you can basically calculate the trace gap and trace width. So, and then what happens next is that in your design rules, you will set the differential impedance to take its value from this impedance profile that we have set up in a board layer stack window. And now, when you route your differential traces, they will use the exact values that are matching the impedance that you target. So the next point about fabrication issues is to always make sure to add plenty of test points, and that is just to make your life easy when you're going to debug the circuit, so you can check them later with a multimeter or an oscilloscope, and you know exactly what to look for. Now, what point I want to make is that you should mark your test points with a silk screen, and make sure you add some sensible identification for each test points. Let's say label it as +1 volt if it's a power supply, or label it as JTAG clock if it's a signal like that. And that just makes sense for you or anyone else who would be working with this board. On a related note, you should also add series resistors to signals, as well as ferrites on power supplies, but you can sometimes omit them in a final design by fitting 0-ohm links instead, if you later find out that you didn't need them. However, it's a really good practice because you don't want to spend hours and days looking for a short circuit on let's say a 3-volt power supply. Instead, you just want to one by one remove different ferrite beads on each IC, and that way you will identify the short circuit much sooner. The number 9 in my list is make sure to segregate components into different blocks. So let's say you have a power supply block, which is a high-speed, fast-switching current, and you may have an analog block, which is audio or sensing circuitry, and you don't want to mix them together, because this is just going to ruin the performance of your analog circuitry, and you want to make sure to locate them at different corners of the PCB, assuming you have enough space for that. I don't have an example of it, but you don't really need one. You just need to pay attention to what you do on a printed circuit board. And this brings us nicely to the final point that I want to make in this video, and that is always make sure to take enough time with your printed circuit board design. And in modern day and age, it became increasingly common to push projects according to 2-week Jira board kind of tasks or assignments, and you just don't have enough time to go over your design thoroughly, and this is very important. To do that and push back on project managers or anyone else who tries to make you work faster. The problem is that people will remember you for your mistakes, but they will not really remember all the times that you did the job right. So you don't want to make too many mistakes too often. Of course you're gonna make mistakes, everyone makes mistakes, but you shouldn't prioritize your project delivery over your project quality. And this is very important. So this is it. That's my 10 points of common fabrication issues. And I hope you learned something new and found this video useful for you. If you enjoyed it, please like and subscribe to this channel, as I will be releasing more PCB and EMC, which stands for electromagnetic compliance, videos in the coming months.